Acid-base chemistry comes into play in the real world in a number of different forms, most notably biochemistry and the environment. And when debating on how to lecture about acid-base chemistry, we could take the perspective of either studying acids or bases. And in trying to deal with this dilemma of how to teach acid-base chemistry, I figured out one day by listening to the radio that this should be all about the base. Just kidding. So why should I care about acids and bases? Well, like I said, environmental impact of acid-base chemistry can be seen notably on statues. This is a gargoyle from the Theater of Notre Dame prior to the fire. And what you can see here is it's been eroded away due to acid rain. The acid rain reacts with the stone and it slowly dissolves. You can also see the effect of acid rain on wildlife. So here we've got a number of fish that have died and washed ashore because the acidity level in the water they lived in became too acidic and effectively they suffocated to death. We can also see the impact of acid rain on just the normal forest. On the left you have a branch that's been in an area where acid rain has been present, and on the right this is a normal healthy tree where it's just natural rainwater. So you can see the acid makes the tree a little bit more sickly in color and kind of washes out its green fur. So we have a number of reasons to care about acids and bases as they apply to the environment. In 1994, this is kind of what the pH or the acidity level of rainwater looked like around the country. Most notably, you'll notice that the East Coast had the most acidic rain, and that is primarily due to the burning of coal for power plants there. So it does contribute quite a bit to the acidity level of the rainwater, and what we see is that areas in that part of the United States are affected much more by the rain than areas on the West Coast where there's a healthier acid level of rainwater. Now, one thing we've done is put zero emission coal plants and scrubbers on the coal burning facilities, and what we've seen almost 20 years later is that we've had a drastic reduction in the acid content of our rain. So as we continue to make strides in pollution control, we should see rainwater return to its natural levels, and events like the dead fish and the discoloring of trees become significantly less. Now, when it comes time to describing acids and bases, we have several different classifications. We have strong acids. These are acids that dissociate completely or 100%. And you may recall what these acids are from the previous semester's course. If not, we will talk about those briefly, but they all have one thing in common. All 7 strong acids have an equilibrium dissociation constant greater than 1. Likewise, all strong bases have an equilibrium constant much greater than 1. Weak acids and bases have an equilibrium constant less than 1, which means only a small portion of the hydrogen ions actually dissociate, and most of the acid does stay associated in the solution. So weak acids, for example HX, only a small portion of it dissociates into H plus and X minus, while the majority of it remains associated in the form of HX. We have molecules that are negligible acids or bases, which really means they don't dissociate it at all. They don't contribute to the H plus concentration or the OH concentration in solution. And we say these acids and bases have a dissociation constant significantly less than 1. Something on the order of 10 to the minus 30, 10 to the minus 40 for the dissociation constant, which really just tells us that this molecule is not going to break apart at all when in solution. To give you some idea pictorially of what a strong acid would look like, we would take something like hydrochloric acid, which has a hydrogen and chlorine bonded, but when we put those into a solution like water, they break apart 100%. That is, looking at the diagram here, you don't see any chlorides attached to H pluses or hydronium ions. They are all completely separated. Something like hydrofluoric acid, on the other hand, is a weak acid, and what we find is that the hydrofluoric acid molecule pretty much stays together in solution. We do see an occasional fluoride ion floating around, so HF is the green and white ball, the fluoride ion is just the green, and over here we see that the hydrogen ion has attached to a water creating H3O+, which is also the same thing as H+, and so we have most of our hydrofluoric acid associated and just a small amount of hydrogen ion and fluoride ion in the weak acid. So what are the strong acids and bases? There are millions of weak acids and bases, but there's only a small number of strong acids or bases. The 7 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. That's it. Those are the only 7 strong ones. On the other hand, we have a number of strong bases, which include sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, barium hydroxide, and strontium hydroxide. Those are the only 7 strong bases. So just remember those 7 strong acids and bases, and everything else you'll be dealing with will be weak by definition. Also, we won't be talking about superacids, which are a little on the scary side in terms of acidity and what they can do. So we'll just stick to basic strong and weak acids. Now, we've talked about acids when we first talked about chemistry and molecules, and we defined acids by the Arrhenius classification. The Arrhenius classification defined an acid as anything that produced an H+ ion, which is also known as a hydronium ion in solution. So we abbreviate H3O+ for H+. It's just a bookkeeping exercise that keeps our lives a little bit easier when balancing equations. While this definition was a remarkable leap in terms of classifying molecules, it did not go to the full extent of being able to define what all acids and bases are. So Arrhenius said, look, any acid is an acid if it creates an H+ in solution. Arrhenius also defined a base as a molecule that increases the OH concentration, or the hydroxide concentration. And while it was a significant step in the right direction of defining acids and bases, it did leave some molecules out of the classification, such as NH3 or ammonia. So a better classification system needed to be developed. And that development came in the form of 2 scientists named Bronsted and Lowry, who didn't actually work with each other, but they developed a better definition of an acid and a base at the same time in 1923. And what Bronsted-Lowry said was, rather than talking about H+ and OH ions, that an acid is anything that donates a proton, which is essentially an H+ ion. And a Bronsted-Lowry base is something that accepts an H+ ion. So it was a subtle difference, but you can see here in the reaction that we could now classify ammonia as a base because it accepts a hydrogen ion from water, leaving behind the ammonium ion and hydroxide.